Today, we're going to pull back the curtain on our digital world to reveal a hidden connection, a secret ingredient that makes everything from your Wi-Fi to deep space communication actually work. It's a fascinating story about a beautiful piece of mathematics and our constant battle for perfect information. All right, let's jump right in.
So, let's start with a bit of a puzzle. On the surface, these two things couldn't be more different, right? One is a picture of elegant, organized structure, and the other is, well, it's just a mess. But what if I told you that the key to fixing the mess is hidden inside the map?
And this lays it out perfectly. On the left, you've got the clean, logical world of graphs, just simple dots and lines that show how things are connected. And on the right, you have the chaotic reality of data errors, where information gets totally scrambled. The bridge between these two, that's where all the magic happens.
Okay, so to solve our puzzle, we've got to get on the same page with some of the lingo. We're going to break down the three key players in this story: the problem itself, the error, and the tools we use to solve it: graphs and codes.
First up, let's meet the villain of our story, the error. You know, in the digital world, everything is just made of ones and zeros, or bits. An error is simply when one of those tiny bits gets accidentally flipped. A 1 becomes a 0, or a 0 becomes a 1. It sounds like a tiny problem, but a single flipped bit can corrupt a photo, garble a text message, or completely ruin a download.
And now for our hero. When I say graph, I don't want you to think of a bar chart. No, think back to that subway map. A graph is just a mathematical blueprint of connections. It has nodes, you can think of those as the stations, and edges, which are the lines or tracks connecting them. It's a really powerful way to visualize how different things are related.
So how on earth does a map of connections help us fix those pesky flipped bits? Well, this is the real breakthrough. We can use the structure of a graph to create a set of rules, a code that our data has to follow. And if the data shows up and it's broken a rule, bam, we know an error happened.
You know, this idea can be surprisingly simple. Let's look at a basic rule called a parity check. Imagine you send 3 bits of data. The code tacks on a 4th bit, the parity bit. Its one and only job is to make sure the total number of ones is an even number. So if the whole package arrives and, oops, there's an odd number of ones, the receiver knows instantly that something went wrong. Simple, right? But it's super effective.
Now that little trick is great for a handful of bits, but when we're talking about protecting the billions of bits in a streaming movie or an online game, yeah, that's just not going to cut it. To do that kind of heavy lifting, we need much better blueprints. We need smarter graphs.
And that brings us to a gallery of some truly brilliant designs. Think of these like different architectural styles for building codes. Each one has its own strengths and its own purpose, but they're all based on the powerful principles of graph theory.
First up is a real powerhouse, a true heavyweight champion of raw efficiency: Low-Density Parity-Check codes, or LDPC codes for short. These are the workhorses humming away inside our fastest communication systems, and their secret lies in their very specific graph structure. LDPC codes use a special graph that separates the data bits from the rule checks, creating this incredible system of checks and balances. Each rule only looks at a few data bits, which lets the decoder work at lightning speed to find and fix errors. They are so good they can get us unbelievably close to what's known as the Shannon limit, the absolute theoretical speed limit for perfect error-free communication.
But not all data comes in one neat little block. Sometimes it's a continuous stream, like a phone call. For that, we need a different approach. And that brings us to convolutional codes. They treat data like a journey that unfolds over time.
The graph for these codes looks kind of like a maze, or a trellis. As the data streams in, it creates a path through this structure. If an error flips a bit, the path gets knocked off course. The decoder then has to play detective, looking at the corrupted path and figuring out the most likely original one. This clever trick is done by a famous algorithm called Viterbi decoding, a foundational technique used in everything from mobile phones to deep space probes.
So we've got codes for speed and codes for streams, but what if your top priority is just sheer brute force toughness? For that, engineers turn to codes built from what are called expander graphs.
I want you to picture an expander graph as a super connected web. It has no weaknesses, no bottlenecks. If you wanted to break a piece of it away, you'd have to cut an enormous number of links. This built-in robustness makes them fantastic for building extremely strong, error-resistant codes, especially when you absolutely cannot afford any mistakes. It's a structure so powerful it's found applications all over computer science.
Okay, so we've looked at some cool mathematical blueprints, but why does any of this actually matter to you? Let's connect this abstract theory to the real-world technology that you use every single day.
I mean, this number is just staggering. The absolute theoretical perfect speed limit for any communication channel was calculated by Claude Shannon way back in the 1940s. For decades, engineers thought getting close was impossible, but codes on graphs, especially those LDPC codes, can get us to about 99.9% of that perfect limit. That's the reason your Wi-Fi and 5G are so incredibly fast and reliable.
And let's be super clear, this isn't just theory. This is the engine running under the hood of our modern world. It's behind reliable Wi-Fi and 5G. It's how we get those crystal clear images from probes millions of miles away. And it's not just the past, it's the future. This very same framework is a foundational tool for building the next generation of technology, including quantum computers.
And this quote really just says it all. This mathematical language of graphs isn't just one tool among many. It's an indispensable, essential framework. It gives us the power to see, to build, and to perfect the very codes that hold our digital society together. From a subway map to a corrected file, the connection is complete.
So, I'll leave you with a final thought. We've just uncovered one profound, hidden connection between some very abstract math and our everyday technology. It really makes you wonder, what other invisible structures and secret ingredients are out there, quietly building the world of tomorrow?